Large language models like ChatGPT and Claude have exploded onto the scene, changing how we interact with computers forever. But how do these systems actually work? How can they write essays, answer questions, translate languages, and even write code? In this video, I'm going to break down this fascinating technology in simple terms that anyone can understand. No computer science degree required. So, what exactly is a large language model? At its core, it's a sophisticated computer program that has learned patterns in human language by reading absolutely enormous amounts of text. Think of it as the ultimate pattern matching machine that's become incredibly good at predicting what words should come next. Imagine you've read every book in a massive library, every website on the internet, and millions of conversations. You'd develop an intuitive sense for how language works, what words tend to follow others, how sentences are structured, and how ideas connect. That's similar to what an LLM does, except it processes far more text than any human could read in multiple lifetimes. The word large in large language model refers to two things: the enormous amount of text data used for training, and the massive number of internal parameters, which we'll explain later, that the model uses to understand and generate language. Here's the surprising part. At its core, an LLM's job is actually quite simple. It predicts the next word in a sequence. If I give you the sentence, "The cat sat on the," you might predict mat, or chair, or floor. You know, these are reasonable completions because you've encountered similar patterns throughout your life. Visual. Probability bars showing percentages next to each word option. LLMs work the same way, but with mathematical precision. They assign probabilities to every possible next word. Maybe mat gets a 30% probability, chair gets 20%, floor gets 15%, and thousands of other words get smaller probabilities. The model then selects from these options, usually favoring higher probability words, but with some randomness to keep things interesting. By repeatedly predicting the next word, then the next, then the next, the model can generate entire paragraphs, essays, or even books. Each new word it generates becomes part of the context for predicting what comes after. But before an LLM can predict anything, it needs to learn. This learning process is called training, and it's where the model develops its understanding of language. First, researchers collect massive data sets of text. This might include books, websites, articles, code repositories, and other written material. For the largest models, we're talking about hundreds of billions or even trillions of words. This text becomes the model's education. During training, the model is shown countless examples of text sequences. The process works like this. 1. The model is given a partial sentence. 2. It tries to predict the next word. 3. The system checks whether the prediction was correct, because the training data includes the actual next word. 4. The model adjusts its internal settings to make better predictions next time. This happens billions of times with different text examples. Gradually, the model learns which words typically follow others, how grammar works, what facts are commonly stated together, and even subtle things like tone and style. Think of it like learning to ride a bicycle. At first, you wobble and fall. But each attempt teaches your brain and muscles to make tiny adjustments. After enough practice, riding becomes natural. LLMs go through a similar process with language, making millions of tiny adjustments to improve their predictions. To understand how LLMs actually work internally, we need to talk about neural networks. Don't worry, I'll keep this simple. A neural network is a computer system loosely inspired by how human brains work. Your brain contains billions of neurons connected to each other. When you learn something, the connections between neurons strengthen or weaken. Neural networks in computers work similarly, but with mathematical operations instead of biological cells. A neural network consists of layers of artificial neurons. Information flows through these layers, getting transformed at each stage. Early layers might recognize simple patterns, like common letter combinations, while deeper layers recognize more complex concepts like the topic of a sentence or the sentiment being expressed. Modern LLMs use a specific type of neural network architecture called a transformer. Introduced in 2017, transformers revolutionized natural language processing. The key innovation of transformers is something called attention. Imagine reading this sentence. The animal didn't cross the street because it was too tired. What does it refer to? You know it refers to the animal, not the street, because you paid attention to the context and meaning. Transformers use an attention mechanism that lets the model focus on relevant parts of the input when processing each word. When processing it in our example, the attention mechanism helps the model look back at animal and determine that's what it refers to. This attention mechanism works across the entire input, allowing the model to consider how every word relates to every other word, even in very long texts. This is what gives LLMs their impressive ability to maintain context and coherence. You'll often hear about models having billions or even trillions of parameters. But what are parameters? Parameters are essentially the knobs and dials that get tuned during training. Each parameter is a number that influences how the model processes information. When training adjusts these parameters, it's like fine-tuning millions of settings to improve performance. A larger number of parameters generally means the model can capture more nuanced patterns and store more information. However, more parameters also mean the model requires more computational power to run and more data to train effectively. Think of parameters like the experience and knowledge in a human brain. Someone with more diverse experiences and education might be able to handle more complex tasks. Similarly, models with more parameters can typically handle more sophisticated language tasks. Here's something interesting. LLMs don't actually read text the way you do. Instead, they break text into tokens. A token might be a word, part of a word, or even a single character depending on the specific model. For example, the sentence, "I love pizza," might be broken into 3 tokens. I love pizza. But a less common word like unbelievable might be broken into parts. Believe, able. Each token is then converted into a series of numbers, called an embedding, that the model can process. This numerical representation captures something about the token's meaning and how it relates to other tokens. The model has a vocabulary of all possible tokens it knows, typically tens of thousands of different tokens. Any text you input gets converted into a sequence of these tokens before the model processes it. Now let's walk through what happens when you ask an LLM a question or give it a prompt. Step 1. Processing your input. When you type a prompt, the model first converts it into tokens, then into numerical representations. These numbers flow through the layers of the neural network, with the attention mechanism helping the model understand the relationships between different parts of your prompt. Step 2. Predicting the response. Based on its training, the model generates a probability distribution for what token should come first in its response. It samples from this distribution, usually favoring higher probability tokens, and selects one. Step 3. Continuing the generation. That first token is added to the context, and the model repeats the process to generate the second token, then the third, and so on. Each new token is chosen based on both your original prompt and all the tokens the model has generated so far. Step 4. Knowing when to stop. The model continues generating tokens until it produces a special end token, reaches a maximum length, or is stopped by the system. This is how it knows when it has finished answering your question. Here's something important to understand. LLMs don't know things the way you do. They don't have true understanding or consciousness. Instead, they have statistical patterns. When an LLM tells you that Paris is the capital of France, it's not retrieving a fact from a database in its memory. Rather, through training on vast amounts of text, the patterns of words associating Paris with capital and France have been encoded in its billions of parameters. The model has learned that this combination of words frequently appears together in its training data. This is both impressive and limiting. It's impressive because these statistical patterns can capture incredibly nuanced aspects of language, reasoning, and even creativity. It's limiting because the model can sometimes produce confident-sounding statements that are actually false. It's simply following patterns without true understanding. One of the most fascinating aspects of LLMs is emergence, the phenomenon where capabilities appear that weren't explicitly programmed. Researchers train models to predict the next word, but these models end up being able to translate languages, solve math problems, write code, and perform logical reasoning. These abilities emerge naturally from the patterns in the training data. Language inherently contains logic, reasoning, and knowledge about the world. By learning language patterns deeply enough, models implicitly learn these other capabilities. It's like how learning to read opens up countless other skills. You can follow recipes, understand instructions, learn history, and more. Reading itself is one skill, but it enables many others. The initial training, called pre-training, teaches the model language patterns, but it doesn't make the model particularly good at following instructions or having conversations. That requires additional training called fine-tuning. During fine-tuning, the model is trained on examples of questions and appropriate answers, or prompts and desired responses. This teaches the model to be more helpful, to understand what humans want, and to respond in conversational ways rather than just completing text. Many modern LLMs also go through reinforcement learning from human feedback, or RLHF. Human reviewers rate different responses from the model, and the model learns to favor responses that humans prefer. This helps align the model's behavior with human values and expectations. Despite their impressive capabilities, LLMs have significant limitations. First, no real understanding. As we mentioned, LLMs work on statistical patterns, not genuine comprehension. They can seem intelligent, but lack true understanding. Second, training data cutoff. Models only know about information in their training data. If a model was trained on data up to 2023, it won't know about events from 2024. Third, hallucinations. Sometimes LLMs generate false information confidently. Because they're pattern matching rather than fact-checking, they might produce plausible-sounding but incorrect statements. Fourth, bias. LLMs learn from human-generated text, which contains human biases. Models can inadvertently reproduce or amplify these biases. Fifth, no persistent memory. Most LLMs don't remember previous conversations. Each interaction is independent unless the previous conversation is explicitly included in the new prompt. And finally, computational costs. Running large models requires significant computing power, which translates to energy consumption and environmental impact. The field of large language models is evolving rapidly. Researchers are working on making models more efficient, more accurate, better at reasoning, and more aligned with human values. Some exciting directions include models that can search for up-to-date information, models that can use tools and interact with software, multimodal models that understand images and video in addition to text, and more specialized models designed for specific tasks. Large language models represent a fascinating achievement in artificial intelligence. By training on vast amounts of text and learning to predict the next word, these systems develop the ability to generate coherent, contextually appropriate